Okay, so welcome back to our lecture on quantum information theory. The last time we discussed quantum algorithms. In particular, what we discussed was Simon's algorithm and quantum phase estimation. We are now continuing with quantum algorithms, and in today's lecture we just discussed the last one for this lecture, which is Groover's search algorithm. And Groover's algorithm is useful if you want to search an unsorted database. So suppose you have a database, suppose it has n elements, and you're searching for an element. And then what you do is, suppose you're given an element and you ask whether this is the solution, then you do a validity check, right? So you ask something, is this a solution or not? And you then specify how fast the algorithm is in how often you have to ask how often you have to do this validity check, right? So now suppose that you are given such a database which is unsorted and you want to find a specific element, then how often do you have to do this validity check, right? If you do it classically, then you have to ask, so the number of times you have to do this validity check scales with the size of your database, so scales as n, right? However, what Groover found out in 1996, that if you do this quantum mechanically, so the number that you have to do this validity checks only scales with the square root of n, which gives you a quadratic speedup. And as an example, you might think of, suppose you're given a phone number and the phone book, and you want to find the name associated to this phone number, right? So the phone book is not sorted by the numbers, so you have an unsorted database, and you want to find the name which corresponds to this number. And then at some point, you have to ask her, is this name a solution? So does this name correspond to this phone number or not? And then Groover algorithm tells you that you have to ask square root of n times in order to get a solution. While if you do it classically, you have to ask n times. Right? So this is, let me write this down. So it's chapter 2.5.4. So suppose we wish to search through an unstructured database of, we have n equal 2 to the n elements. Which are labeled by 0 to 2 to the n minus 1. So once we found, or once we are suggested a solution, it's easy to verify or easy to check whether this is a right solution or not. So it's easy to check its validity. But it's difficult to come up with the solution to start with. It's difficult to find the solution. To start with. So in the example of the phone number in the textbook, suppose you're given a name and then it's easy for you to check whether this is the right name for this phone number because the phone book is sorted by name, right? So it's easy to check the validity. But to get the solution to start with, it's hard because you have an unsorted database. So now, classically, this takes O(n), so it's n is 2 to the power of n here, O(n) validity checks. To solve the validity checks, and Groover showed in 1969 that using quantum mechanics only O square root of n operations are needed. So let's now see how this Groover algorithm works. And for this, suppose now that we are given a register of n qubits, and meaning that we have in total 2 to the power of n states, and we now label these numbers. So we label our elements of the database by these numbers, right? So that we can associate each number with an element of our database. So we consider a register of n qubits to represent the database with n is equal to the n labels and further we consider a single oracle qubit so in addition to these n qubits which represent the database, we also consider one single oracle qubit. Okay, we're going to see in a second what this does. And then we have an oracle, and the oracle tells us. So we give the oracle an input, which is an element of the database, and the oracle then tells us whether this is a solution or not. Right. So meaning that we can quantify how fast the search algorithm is by asking how often do I have to call the oracle. Right. So how often do I have to ask the oracle whether this is a solution or not. Right. And this oracle always tells me, okay, this is a solution or this is not a solution. So the oracle verifies whether a given label is an element of the set of solutions. Hence, the speed of the algorithm is determined by the number of oracle calls. Okay, now let's get a bit more serious. First, let us define what the oracle does, right? So suppose now for x, state vector of the database and y, a state vector of the oracle qubit the oracle operation acts as follows. So if we have x, y, so this was our n bits, x are n bits from our database, and y is a single bit, which we call the oracle bit. If now the oracle acts on this, then we get x and y o plus f of x. So this is again the addition modulo 2. This equation 2.131. So and what is f of x? It's 0 if x is no solution, and it's 1 if x is a solution. So by this you see that the oracle tells us whether we have a solution or not. Okay? And it writes in this oracle qubit, it says, okay, it writes down whether it's a solution or not. And in the end, what we do is we then quantify in the end how fast this algorithm works by how often do we have to call this oracle. Because the oracle tells us is it a solution or not, and the speed, as we wrote it down here, the speed is determined by how often we ask this question. So now we do a trick, namely a trick which is the same trick as we've seen for Deutsch's algorithm. Okay? We now input the minus state, or we use the minus state as the oracle qubit, which is 0, -1. For this implies that x minus, so if the oracle acts on this one, we have -1 to the power f of x, x minus. So, and what you see here now is, since we use the minus state for the oracle qubit, it doesn't change, right? And due to the fact that this oracle qubit doesn't change, we can disregard it. That's the same thing that we've done in Deutsch algorithm. We prepared a qubit, which is kind of a working qubit in the state, and it always remains in the state. So we can disregard this qubit. So this is such that y equals minus can be disregarded. And we can compactly write this simply as the oracle. Now I denote this operation by O. What does this operation? It takes x to -1 to the power of f of x times x. Okay, so this is exactly this operation, but we now disregarded this oracle qubit because it's simply a working qubit which does not change. Once we prepare this in minus, it always remains there. So this is equation 2.134. Okay, now this now describes how the oracle works. And let me now show you how the circuit of Gruver's algorithm looks like. And then we go step by step through the circuit. Okay? So the circuit of Gruver's algorithm looks as follows. So we start with our qubits in 0. So these are n qubits, which is our database. Okay, and then we have a single oracle qubit. Okay, and the oracle qubit we want to set to minus. Okay, how do we get this to minus? First, we make an X operation, so a NOT operation, such that we get 1, and then we Hadamard, and then we're there, right? So this one, we first have a Pauli X gate, and then we Hadamard, and then we have a minus state here. Right? And now the other qubits, well, you can actually almost, I guess you know what we do first, we Hadamard them, right? So as always, we make a Hadamard on each qubit, and then we are in a coherent superposition of all possible states, right? And the next thing is we then perform this what we call a Gruver iteration, and this involves the Gruver iteration involves the oracle. We will see this in a second. So let me call this G. Okay, and this G, as I said, involves the oracle. And what this tells us, okay, first we put the state of our database into a coherent superposition of all states, and then we have to distill those a solution of these states, okay? Because this is now a superposition of everything, and we want to distill now this solution. And we distill this by successively calling this Gruver iteration, okay? So we have G here, and then we again have this G operation, okay, and then again, and again. And in the end, what we want to specify is how often we have to do this Gruver iteration. This is one aim that we're going to do. And at some point, we are done. Okay. So we call this Gruver iteration several times. But we still have to specify how often. And now I want to specify how this Gruver iteration looks like. So first let me name this 135. Okay. With the Gruver iteration, I think I get this here. So this was our database. Okay, this is too small. Sorry, I have to use another board. this was the database. This was the Oracle qubit. And this is equivalent to the following. So this is first we call the oracle. Okay, and we specified the oracle here in this equation. And then we Hadamard those qubits from the database. Then we perform the following operation, namely 2 times the project on 0 minus identity. Well, and what this does is it gives a phase shift of -1 to each basis state except for 0. For 0 it remains +1. Okay, that's what it does. We're going to see what this does in a second. And then we again do the Hadamard on each qubit, and that's it. Okay, and nothing on this oracle qubit. And here you see now that the only thing that from here on acts on this oracle qubit, so here we have minus, and the only thing that acts on this oracle qubit is the oracle itself, and the oracle is such that this qubit remains unaffected. Okay, that's why we can disregard it. So it's always in minus here. Okay, let's now see what this does. First of all, let's calculate the state before the first groove iteration. Okay, we already know the oracle qubit, and the qubits of the database are easy to calculate. So let's first call the state here at this position, and then we see what these groove iterations do. Okay. So before the first groove iteration, the state of the database is, so we have Hadamard acting on 0, and this we know is, we call this, let's call this psi, and this we know is the sum over all x from 0 to 2 to the n minus 1 of x. So it's a coherent superposition of all states that we have. Okay, I forgot this to give a number. It's 2, 136, and this is 2, 137. Okay, so as I said, before the first groove iteration, we are in a superposition of all states, right? And there are some of them are possibly solutions. Okay, there's possibly more than one solution. There can be one solution or more solutions. And now with this groove iteration, we want to distill out the solutions from this state. Okay, and to see what these groove iterations do now, let's first calculate what a single groove iteration does. Okay, so this is the single groove iteration. We have first the oracle and then this part here. So let's start with this part. So with the Hadamard and then this operation in the Hadamard. Okay, let's start with this. So operation h tensor n to 0, 0, minus 1, h tensor n on the data base qubits is, okay, we can rewrite this a bit. And after rewriting this, we're going to see that this can be illustrated. So let's now act with this Hadamard gate on this state. So we have 2 times Hadamard on 0, and here the same. And then we have minus Hadamard times Hadamard. So we know that it's self-inverse, so this gives the identity on the right-hand side. And on the left-hand side, we know that this is simply the state psi that we have here. Right? So this gives us 2 times psi minus the identity. Such that the Groover iteration performs the operation. So now we call this G. So it does this here, 2 psi minus identity, and before that it does the oracle call. So this is 2,139. Okay, now we want to visualize what this does, right? And I'm going to tell you how we can visualize this. So first, we're going to take this part here, and there we see that there's going to be a reflection of a state by the state psi. And for the oracle, we will also see that this similarly is also a reflection. So this operation we can really illustrate in terms of reflections. Okay? And this is what we're going to do now. So once we see how this acts as a reflection, what we then do is reflections, because this Groover iteration acts several times, right? So we then see that this reflection happens more often, meaning in the end it's going to be a rotation. If you have multiple reflections, it's going to be a rotation. And with this rotation, we can then specify what this bundle of Groover iterations do, and then we can find out how often we have to call this Groover iteration. So this is the aim this is what we're aiming for. Therefore, we first take a look, okay, how can we illustrate what these operations here do? So I'm going to erase now this circuit, but I think it's easy to remember that the only thing that we do is successively applying the Groover iteration. We're doing nothing else than that now, okay? Because this state we described, it's easy to describe, and now we only do Groover iterations. And here we have how the Groover iteration operation acts, right? So with this, we can now erase this circuit without any worries. Okay, so in order to visualize the action of the Groover iteration, first consider the action of, what is it, 2,138 on on a general state phi. So we act now with 2 times psi minus identity on phi. Okay, what we get is 2 times the inner product of phi and psi minus phi. So this corresponds to a reflection of phi with respect to psi. So let's visualize this. Suppose we have suppose this here is phi, and this one here is psi. Then we have then we have 2 times this overlap minus phi. So this overlap is given here. So this is the overlap psi phi. And then say again here the overlap psi phi. Then we are somewhere here. And then we go to minus. Not so nice. Like this. This is minus phi. And what we end up with is this reflection. Okay, didn't draw it very nicely. And here we then have 2 times psi phi minus phi. Okay, and what you see is that this is simply a reflection with respect to psi. So we reflect this down here. Okay, so here we have this distance is given by this inner product. And then we take this 2 times, so we have the same thing here. And then we go with minus phi down there. So we have a reflection. Meaning that the action of this operator here can be now visualized simply by this reflection. Right? So we know the first part of our groove iteration. We know that this can be illustrated by a reflection. And we're now going to see that the second part can similarly be illustrated by a reflection. Right? So this is the next thing that we do. And for this, we now have to subdivide our space into 2 subspaces. So let me first write this down. So likewise, the operation O can be understood as a reflection to this end. Decompose the Hilbert space into 2 subspaces. Or into the subspace. Let's call this S, which contains all those elements which are a solution to the problem. contains all solutions. So these are the states X, where X is an S. So this is the set of all solutions. S, and the subspace call this S bar, which contains, okay, I didn't say how many there are, which contains all n solutions. So suppose there are m solutions in the subspace M bar, which contains all n minus m states which are no solution. Okay, so what we did is now we took all basis states of our Hilbert space, we subdivided them into those states which are a solution to the problem. So there are m such solutions. Okay, and we say if x, so all those x in S are solutions, and those states which are no solutions, so meaning n minus m states are no solutions, and we call this subspace S bar. Okay, and we can now write our initial state, this psi, you see this is a superposition of all states. We can now write this as a sum of two terms, namely one term of the sum of all solutions plus a term where we have the sum over all states which are no solution. Okay. So then define the states alpha and beta on these subspaces. So we have alpha is equal to 1 over square root n minus m times sum over x is no solution and beta is 1 over square root of m sum over x in solutions. Okay, so we define now the state alpha as the superposition of all states which are no solution, and beta as the superposition of all states which are a solution, right? And with this, it's now easy to see how the oracle operation acts on the state. Because we know that the oracle, what it does is it puts a minus sign in front of a state which is a solution and leaves those states which are no solution unaffected, right? So then it is simple now to see how this oracle operation acts on this state psi. Okay. such that if the oracle acts on, say, a state alpha alpha plus beta beta, with alpha and beta now some coefficients, then we get alpha alpha minus beta beta. And this we can now again illustrate geometrically as a reflection. Now a reflection with respect to alpha. Okay. So geometrically, this is a reflection of alpha alpha plus beta beta with respect to alpha. So let's see this a bit shorter. Let's say this. So this is alpha and this is beta. Suppose now in green. Suppose this state is alpha alpha plus beta beta, and then we have this state being alpha alpha minus beta beta. Okay, so we see now that the action of the oracle can also be illustrated by such a reflection. And what we're going to do after the break is we're going to put these two things together, okay? Because our Groover iteration operator was first this oracle operation and then the operation of this operator here, okay? And we can then combine this reflection with this reflection. And what we get is, with two reflections, we get a rotation. Right? So after the break, we're going to see that by doing first this rotation and then this rotation, we get simply a rotation. And this is what the Groover iteration does. It rotates. And then, in the end, we have to decide how often we have to evaluate this Groover iteration, meaning how far we have to rotate. This is what we see after the break. So let's meet in 10 minutes. Okay, let's continue. Before the break, we've seen that the Groover iteration can be decomposed into two reflections. So those two operations can be seen as reflections. The first part was this 2 times the projector on psi minus identity. Right? And we've seen that this is simply a reflection of this state phi by psi. Okay? So here we have phi, and if we act with this operator on it, so it's reflected by psi. Similar, the oracle operation, there we have seen that this also can be illustrated by a reflection. Now this is a reflection of psi by the state alpha. Right? And alpha was the state which is the superposition of all states which are not a solution. Right? And beta is the superposition of all states which are a solution. Okay? And what we do is now we combine these two operations in order to illustrate what the Groover iteration does. Right? And so altogether, the two reflections O and this 2 times projector on psi minus identity acting on this state psi, which is this coherent superposition of all basis states. Okay, that's factor 1 over square root of 2n x, and this we can write as n minus m divided by n times alpha plus m divided by n minus, n times beta. Okay, so we now simply wrote, we split the sum into those parts which are no solution and those which are a solution. And now we can see how these two reflections act on the state. So acting before the first groove iteration. Can geometrically be visualized as follows. So this is equation 143. I think I'm going to use the other blackboard here. So suppose this is our initial state psi. And now, for the groove iteration, the first thing that happens is this oracle operation. And we've seen that the oracle operation is a reflection with respect to alpha. Okay, so let's do this first. Let's reflect with respect to alpha. Then we are somewhere here. So this gives O psi. And then the second item of this groove iteration is now this operator here, which is a reflection of this state vector by this state psi. Okay? Psi is here, so it's a reflection with respect to psi, so we go up there. So this was not so nice. So we're here. So we end up here. And here we have then G psi, which is 2 psi minus identity O psi. And what you see is that if we have here this angle, say, theta half, and then we have here the angle theta half, and this then must be the angle theta. Okay. So right angles are here and here. First this reflection down here, where we reflect with respect to alpha, and then we reflect with respect to psi, so we go up here. And you see already here now that these two reflections together give a rotation, right? And they give a rotation of psi by the angle theta. So now let's take a look at this equation here. So we see that. Okay, I wrote down now here this. I defined the theta here in this illustration. So if we compare now, then we see that the cosinus of theta half is given here by the square root of n minus m over n, and the sinus of theta half is given by this one here. So by equation, this is 143. We have that the cosinus of theta half is square root of n minus m divided by n, and the sinus of theta half is square root of m divided by n. And consequently, we have that if G acts on psi, we have cosinus. Okay, now we have the part which is the coefficient which is in front of alpha has now here, since we have the angle 3 theta half, we have cosinus of 3 theta half alpha, and then the sinus of 3 theta half beta. And here you see that that we rotated, so we rotated now the state psi by the angle theta, and we got this state. And what's interesting to see is that this Gruber iteration merely happens in the plane spanned by alpha and beta. Okay, so we restrict it to this plane, and we can illustrate everything that happens here with this Gruber iteration in this plane. And of course, it's also easy to see now that if we apply this Gruber iteration again, then we have to do the same procedure. Again, rotate by theta in the end. Okay, so this is what we do. First, let me write down what the angle theta is. So by comparing these two equations here, this is 144 and 145. We have that theta is equal to the arccos, it's 2 times arccosinus of square root of n over n. So let us now combine several Gruber iterations. So by applying G multiple times, we get, after k Gruber iterations, that G of k is equal, acting on psi. Okay, so here you see that we acted once, and what happened is we rotated by the angle theta, so what's in here is theta plus 1/2 theta. Okay, so if we act k times with this operator, then we get cosinus of k times theta plus theta half, okay, because we started with theta half, and then for each time we act with k, we get an additional angle theta, and sinus of k times theta plus theta half. So this similar, same as 2 times k plus 1 theta divided by 2 alpha plus sinus of 2 times k plus 1 theta divided by 2. Let's now illustrate this for k equals 4. suppose now this is psi. And now with the first Groover iteration, we go down here. So we reflect with respect to alpha, and then we reflect with respect to psi. So we get that up here. So this is G psi. And then we do the same thing. First we reflect with respect to alpha, so we go down here. And then with respect to psi, so we're here, this is G squared psi. And then again we reflect with respect to alpha, so we go down here. Now it's getting hard to draw. And then with respect to psi, so we go up here. So we have G power of 3 psi. It's this one. Then the same thing again. We reflect with respect to alpha, so we go down here. And then with respect to psi, we go here. So this is G to the power of 4 psi. Okay, and let's stop then. This is beta. So what you see is, so here we have theta half, and then here we have theta, again theta, theta, and theta. Okay, so each time we act with the Groover operation, we simply rotate by the angle theta. And if you do this 4 times, for this example here, we end up here. Okay? Now you see that if you do it even more often, then we rotate even further. But what is actually the aim? So the aim is to get a solution, right? And the state beta was the superposition of all solutions. So what we want to do is we want to rotate so far such that we are as close as possible to beta, meaning that if you perform a measurement, the probability to get the solution is very high. And if you're exactly at beta, then the probability would be 1, right? But we are possibly not exactly at beta, but somewhere close, meaning the closer we are to this axis of beta, the higher is the probability to get the solution. Meaning that we now have to specify the number k, how often we rotate, so the number k here, such that we are as close as possible to beta. So the optimal solution to the search problem is then achieved for k such that the amplitude of beta is as close as possible to 1. So what you want to do is, let's see, here's beta, this is the amplitude, okay? It's as close as possible to 1 if we are close to this expression being pi over 2, okay? Because the sinus of pi over 2 is 1. So we want this argument of the sinus to be pi over 2, okay? So we want to have 2 times k plus 1 theta over 2. Sorry, yeah, to be pi over 2. So meaning that we have k times theta equal pi half minus theta half, or k is equal to pi over 2 theta minus 1 half. Okay, so now we have a number for k. Of course, this is not necessarily a natural number, but we have to find those k which such that we are as close as possible to this number. And this implies now that the integer, let's call this k naught, closest to this number, to pi over 2 theta minus 1 half, achieves the largest probability to find a solution. Measurement of the output state. We can now explicitly give explicit expression of this k naught. So k naught is the minimum of k in n such that k plus 1 half is greater or equal to pi divided by 2 theta minus 1 half. So you might be confused why k plus 1 half, right? And this we can illustrate. So what you do is we take the minimum k naught such that k plus 1 half is greater or equal to this. So the reason that we have here plus 1 half is because we say that this is greater or equal. Okay? And we can illustrate this as follows. So suppose that, let's draw this, go back to this picture here. We have beta and here alpha. And suppose that we do some rotation, and at some point up there. So this region here, this region we can reach is the region of g to the power of k naught psi. Okay? So if we have the optimal number j naught, then we are somewhere here in this region where this angle is theta half and this also theta half. So we are at maximum theta half away from the optimal point, right? And if you now suppose that we perform j naught plus 1 half such operations, okay, this is strange. You can think in theory about this if you kind of insert into this equation a k naught plus 1 half. Okay, this you can do. So, and then this k naught plus 1 half would live here in this region. So this would be g k naught plus 1 half psi. So again, here we have psi over 2. And now you see that why we write it down this way, because it's the minimum k naught such that this is greater or equal to this. Okay? So this is the optimal. The optimum is here, but we are now greater or equal to this. So on the left-hand side. That's why this plus 1/2 must go in there. Okay, so meaning that we have an expression for the optimal k naught such that we are maximum theta half away from the optimum solution. And this allows us also now to specify an upper bound for the probability to find a solution, right? Because we know that this one here, so this is the sinus of theta half. Let me use another color. So this is sinus of theta half. And this sinus of theta half gives us an upper bound for the error. So after k naught iterations, let's write this down. After k naught iterations, state g k naught psi is not further away from beta than theta half. Hence, the probability to detect a wrong solution well, the probability to detect a wrong solution is bounded by this sinus square of theta half. Right? Because this is the probability that we measure state alpha. So. Hence, the probability to detect a wrong solution is bounded by the probability for, let's call this error, is smaller or equal to sinus squared of theta half. So this is this one here. So this gives us a projection on alpha, and the modulo squared thereof gives us the probability that we find some state in this superposition alpha, so meaning that this gives us an upper bound, right? So this is equation 150. Okay, now next what we want to find out is how does it scale now? So how many Groover iterations do we have to perform? And therefore, we go back to this equation here, and we insert the theta here now. So from equation, this is 148, we find that k, insert this k is equal to pi over 2 theta minus 1/2. And now we insert for theta we had 2 times the arccosinus of square root of m divided by n minus 1/2. Okay, and this we can now approximate using that. So what we use that the arccosinus of x is greater or equal to x for x greater equals 0. So meaning this is smaller or equal to pi divided by 4 times square root of m over n, which is pi divided by 4 and then square root of n divided by m. So, and with this we get our scaling law, because we see that k must be smaller or equal to the square root of n divided by m. Okay, and this tells us that we have to call we have to perform this Groover iteration, meaning we have to call the oracle at most square root of n over m times. Hence, the Groover algorithm converges after O square root of n divided by m oracle calls. Quadratic speedup compared to classical algorithms. Which require O n over m oracle calls. Okay, so this is the Groover algorithm, and there's one thing that we should note, namely, in order to get this optimal k, so k naught, we must know m, and m was the number of solutions, right? So for the version that I just presented, we must know how many solutions there are in order to get this optimal number k naught. Okay, but there are now modifications of these algorithms for which you do not need the prior knowledge of how many solutions there are. And still you find the solution with the scaling O square root of n divided by m. Okay? So there are modifications of the algorithm that I just showed, with which you can find the solution with this overhead, even if you do not have prior knowledge of how many solutions there are. Right, and then there's one more thing, namely, one can show that the Groover algorithm is optimal in the sense that there's no better algorithm. Okay, you cannot do this task faster than O square root of n divided by m. And possibly you're going to prove this in the exercises. I'm not sure, but possibly you're going to prove this. Now there are 10 minutes left, and I think in these 10 minutes we can do the Groover search generated by a Hamiltonian. Okay, so we can now, with this, we are done with the Groover algorithm. Okay, and what we next do is, for the remaining time today, is we're gonna ask, okay, is there a Hamiltonian which can generate this Groover iteration? Or all Groover iterations, actually. Okay? So what we've seen is in the circuit is we initialized our state, we put this into a superposition, then we had a stack of Groover iterations. And now and this stack of groove iterations is actually nothing else but a unitary, and a unitary can be generated by a Hamiltonian, right? And we now ask, okay, is there such a Hamiltonian which generates this, and how? And Hamiltonian is then given, with the Hamiltonian we find a unitary by the time evolution, and then we ask, okay, how long do we have to apply this Hamiltonian such that we get the corresponding unitary and find a solution with certainty. Okay, this is just an additional add up to this topic of the Groover algorithm. So it's the Groover search generated by an Hamiltonian. So the Groover iteration or the rotations due to the Groover iterations, they can be generated by the Hamiltonian namely H is equal to beta plus psi with this psi being our initial state, which we wrote as alpha plus beta, where we had alpha is equal to n minus m divided by n and the square root of, and beta being m divided by n. And they satisfy that modulo squared of alpha plus, or actually simply alpha plus alpha squared plus beta squared is 1. So in the representation, let's now write this state alpha as 1, 0 and beta as 0, 1. So this is simply a representation that we choose. With this we can represent this by 2 by 2 matrices. The Hamiltonian which is 2, 1, 50. So the Hamiltonian 2, 151 reads. So first we write this beta times beta in this representation, which is simply this matrix. And then we write this state psi, so the projector of this, which is nothing else but alpha squared, alpha, beta, and beta squared. So we add this together and use that alpha squared is 1 minus beta squared. So we have 1 minus beta squared alpha, beta, beta squared. Well, sorry, 1 plus beta squared. And then we see this is the identity plus beta times, okay, this we have alpha x minus beta z. Okay, so we can write this as 1 plus beta and then a unit vector n times sigma, where n is equal to alpha 0 minus beta. So this is a unit vector, because we know that alpha squared plus beta squared is 1. And now you see that this is a form that we've seen several times so far. This is equation 2.153. And with this form of the Hamiltonian, we can now write down a unitary given by the continuous time evolution when this Hamiltonian acts. So the first thing we do is we set h bar to 1. So with h bar equals 1, this generates the unitary so we have u equals e to the minus I th. Now we insert this h, so we have e to the minus I t and then identity plus beta and sigma, which gives e to the minus I t and then e to the minus I beta n sigma. And this we know, this is for this we know an expression in terms of sinus and cosinus, namely this is the cosinus of t is missing, sorry, beta t n sigma, so it's cosinus of beta t identity minus I sinus of beta t times n sigma. Okay, so now we have a nice expression of the unitary. Now we can act with this on the initial state. So the unitary acts on the initial state, which was psi, as, okay, I can write this down here, u psi is equal to e to the minus I t, and then we have cosinus of beta t times psi minus I sinus of beta t times n sigma psi. Okay. So now we calculate this here, n times sigma psi. And this we can easily do actually in matrix representation. So for n we have alpha 0 minus beta, and this vector sigma are our Pauli matrices x, y, and z. and psi was alpha beta. So it's alpha times alpha, and alpha was 1, 0, which is up there, and beta is 0, 1, right? So this is psi, and this is n times sigma. So this gives alpha x. So we have here some alpha, and then minus beta z. So we have minus beta beta times alpha beta. So this gives 0, and this gives alpha squared plus beta squared is 1. So this is nothing else but beta. So using this in this equation here in 155 yields that u psi is equal to e to the minus it, and then we have cosinus of beta t psi minus I sinus of beta t beta. Right, and what we want to do is, we now want this time evolution to run so long such that this amplitude is maximum, right? And it is maximum if beta times t is equal to pi over 2, right? And since we are now in a continuous time evolution, we can exactly find such a time such that this amplitude gets 1. So hence, with beta is equal to square root of m divided by n, we find that after t is equal to pi over 2 beta is equal to pi over 2 times n over m, the solution beta is found with certainty. Okay, so what we've seen is that for this stack of Groover iterations, there is an Hamiltonian, which we just wrote down, which generates a unitary operation implementing this rotation. Okay? And we've then seen that since if we do simulate this, we possibly have a continuous time evolution, then we can find a time such that we find with certainty a solution, right? Because we can find the time such that this amplitude is equal to 1, and then we are certain that we find a solution, because all the solutions are stacked together at beta. Now it turns out that you can, of course, think, okay, can I implement this unitary transformation via a circuit? Or can I implement this simulation of this continuous time evolution via a circuit? And it turns out that, well, you can do it, but you won't be better than a Groover search algorithm that we discussed before. So in a sense, Groover search algorithm is optimal. And as I already said before, you can also prove that it is optimal. So meaning that Groover search algorithm, which gives you a scaling of O square root of n divided by m, is optimal. And it's not needed that you do this this continuous time evolution, but you can possibly come up with a nice algorithm to do so. Okay. And with this, I'm at the end for today. And after the Pentecost break, we're then going to start with a new chapter and discuss quantum information. So I wish you a happy holiday and see you after the break.